here. So if I said you cleave this with glycine, you should be able to draw out a peptide where it gets cleaved right here. Right here's the C-terminal side, right, of arginine. So that's where trypsin would cut. Now, what if I said, do I even have anything else on there that will cut at? Chymotrypsin, where will chymotrypsin cut at? Could cut at chymotrypsin, will cut at tryptophan, right? W. So, we go here, this is where it should cut, right? That's where chymotrypsin will cut. So you can see where they're cutting, right? It's cleaving, it's hydrolyzing that bond. It's taking it from an amide bond back to what it originally started as an amino acid.
Is it specific to one area? You also have a tyrosine as well.
Yeah, it would cut here too. It would cut here. Right there.
Chymotrypsin.
Chymotrypsin. So you can see how it could get much more difficult if I get a long protein that would cut in multiple parts. It would be harder to piece them together. And so for a long peptide like this, you would need enzyme degradation to help you kind of fill in the blank. Well, you could use just the cutting to figure out where things are relative to one another. You could piece it together. You could say, okay, if I cut with this, I get a trimer, but it would be much harder, right? And you might never be able to get it exactly right. So draw peptide, show the pH. We talked about peptide cleavage. There's something that I want to go over with you guys because I think, I don't know if you guys grasp this concept because it goes to the core of deciding whether or not that's proteinated or not. Okay? So let me just draw up real quick. This is your general acid-base stuff. I know it might not be the topic you want, but it should help you understand where I'm coming up with how I decide this. So what's something that I had to do on your homework? I had you draw what for an amino acid? What fits in with the water section with amino acids? Acid-base titration curve, right? In your acid-base titration curve, what do? We titrate in hydroxide, right? We titrate in hydroxide, and we use this term equivalence. And hopefully you know this from, I think, general chemistry, where equivalent is how much you need to add to have a certain stoichiometry of reactant, have two reactants together at certain stoichiometries. And then we look at the pH, right? And we know the pH is 2, 4, 6, 8, 10, 12, and we go up to a 14-point scale. Okay. Now, what amino acid would you like me to draw a pH titration curve? Arginine? Arginine? Tryptophan? Tryptophan is not cool because it only has 2 ionized groups, right? So tryptophan is cool to draw, but not cool for pH. So let's do what was the other? Arginine? Arginine. So the first thing we need to do with arginine is we start out in its completely protonated form, right? 1, 2, 3. So those are memorized.
Okay, it's not
The
like when we're having to fill out like a chart, we're doing like when we're deprotonating it, you'll give us like 2 points, like on the homework you gave us like.
Oh, well, I give you the.
Get an actual focus.
I give you the bars, but I don't give you the That's something you remember. Remember the table I gave you? 2, 4, 6, 8, 10, 12, right?
Yeah.
That's for you to remember these things. So 2, right, is what? Alpha carboxy, right? 4 is what? There's 2 that fall into that category. Aspartate and glutamate, which aspartate you can think of as 3.8, glutamate 4.2, so they average out to 3. Okay, 2, 4, 6. Which one's 6? Histidine. And then 8 is cysteine. 10.
Well, 9.5 is amino.
So yeah, 9.5.
And
The
then
tyrosine
and then
is 10.5. So the 9.5 and the 10.5. And then 12.5 is arginine.
Okay.
So that's just, that was something I said up front. This is something for you guys to use as a way of memorizing.
So, I mean, so you're saying the first thing that gets carbonated at 2 would be the carboxyl group.
So you start out in the most protonated state, and automatically what you typically do is, what's the most acidic one? That's your first pKa, pKa1. That's going to be the most acidic one. So if we were to start out in a fully protonated form where we're at pH 0, imagine that, 0, right? All these protons all over, right? Lots of acid. We would draw this out in that state, and then we would say, okay, what's the pK of the alpha carboxyl? What's the pK of 2? And the reaction that occurs as we start to add hydroxide is that we shift the equilibrium once we get to a certain point from being NH3 plus, right? And a protonated carboxyl group, and then our amino group up there. The first one that's the most reactive, right? That's the most acidic is this one. So what we're doing is we're dumping in hydroxide into a solution with this molecule. And then once we reach a specific pH, what happens is we start to react with the most acidic proton. Hydroxide is going to pull that off, right? And so that's why we get this. 1, 2, 3, nitrogen. Okay, so that would be the first step. So what's happening here? Right off the bat, we're starting to add hydroxide to this, okay? And what happens is the pH jumps rapidly until it gets to 1 because there's nothing reacting with hydroxide. It's just sucking up, it's just sucking up protons in water. So it's changing the pH of water. But once it gets to 1, what happens is it starts to slowly increase. Okay? So we have this rapid rise, and we get this slow, gradual increase, okay? Because what happens is we start out here, and then once we hit pH 1, right, plus or minus 1 of the pKa is the buffering region. So that means at 1, this is going to start reacting with the hydroxide. Before that pH, nothing's going to happen. So you see it as a rapid increase, and then we see this reaction occurring. What you can think of is hydroxide being added to this, reacting with this, making water plus the conjugate base, right? That's what's happening in the buffering zone. There's a reaction going on, okay? And then what we do is we gradually go up, right? And we know that the pH is equal to the pKa, where? When there's 50% of this species and 50% of that species. That's where we call the half equivalency point, where we've added enough hydroxide to convert 50% of this into its conjugate base form. So you have a 1-to-1 ratio. So that's where we get sorry, my eyes, I'm looking down. And so after that point, right, up until, so starting at this point at where the pH is 1, that's where we start with 100% of the acidic form, the acidic form. And then as we're gradually rising, we're shifting that equilibrium to having more and more conjugate base. Okay? And then so we keep doing that until we reach this half equivalency point. That's where we have 50% of this, 50% of that. And then we keep gradually rising because the reaction still goes until we get to 1 equivalency point. And And at that point, we should be at about a pH of 3, right? Because the buffering is within plus or minus 1 of the pKa. Okay, now the next thing that reacts is the next most acidic, and that would be here, the amino group, right? pKa of that is 9.5, right? And so pKa2 is going to be 9.5, and that is what's going to be depropionate. So the hydroxide reacts with the most acidic in first. That's why I always have you draw it out to the spectrum. And H2 plus, I'm sorry, I'm running out of room. I'm going to erase this. Okay. So that's the next thing. So now what's going to happen? The pH is going right after it gets past this 1 equivalent. The pH has to shoot up because there's nothing reacting with water or with hydroxide. It's just pulling out protons out of water, increasing the pH. So at 1.5, that's where we have 50% of this, 50% of that. So we go in here, we go up to 9.5, just somewhere right around here. So in between that, this is going to have to rapidly shoot up very quickly. Okay, until it gets to about pH of 8.5, that's where the buffering region starts. And then so we start to gradually rise, and we go from 8.5 to 10.5, which is somewhere around here. It reaches that, and then it has to go up again. Right? The buffering region is from 8.5 to 10.5, right? The midpoint of that is 9.5, that's pKa2, right? Where the pKa equals the pH. Now we've got a third one, right? And I don't care if you forget to put in the hydrogen, it's assumed. Okay? And so the last one, the next most acidic, right, is up here. 1, 2, 3. So we've lost that proton, right? Say this, NH. We've lost that one, and now we're at a neutral. Imidazole, and that's a guanidino group. Let me make sure I get my charges in here. pK of that is equal to 12.5. So at 11.5, which is somewhere right around here, we should rise up quickly to that point, and then our 12.5 should be at the 2.5 here. So we have that reaction going, and it's going to gradually rise until 3, and then it just goes straight up and skyrockets. Okay? So we have these buffering zones, right, which are plus or minus 1 unit of the pKa and the pH range, and that's where they're undergoing this interaction with one another. And so that makes perfect sense. Why isn't it shooting up? Because there's a reaction here where hydroxide is pulling off those protons, and instead of just raising the pH, it's making water. Okay? And on each side of that pKa, what it's telling you is on this side, I have more of the acidic form. On this side, I have more of the basic form. And then right in the middle at those half equivalency points is where I have 50-50. Right? And all of this is described by the Henderson-Hasselbalch equation, right? pH equals pKa plus a log A minus over HA. Right? And this is directly derived from, right? It's derived from the equilibrium equation for the different acid groups, right? This is just a rearrangement of the acid equilibrium equation, right? For this one, we have an equilibrium equation. For this one, we have an equilibrium equation. For this one, we have an equilibrium equation. So we can only use this equation when we're in the right zone, right? That's why, right, we pick out when we want to make a buffer, and we want to make a pH 10 buffer. Which one would we want to use? Would we want to use these forms? No, there's no buffering in that zone at pH 10. We'd want to go here, right? Within that zone, within the 9.5 zone, if you add acid or base, right, what's going to happen? Not much change. So that's how the buffering works, right? You're adding something that will react and suck up any hydroxide or acid that's added. Yep.
Alright, so the buffering zone is going to occur plus or minus the pKa.
One of the pKa, yep.
So the buffering zone for the first one will start at around 1.
Yep.
And then we go all the way up to around 3.
3. And then after that, it shoots way up.
Right. And the other will be start around 8.5.
8.5.
And all the way to
10.5. That's where that's why, I'm showing it, there's not much change there because it's buffering in that region. And so this drawing that we've been working on is really to depict and show you what buffering really is. Buffering is really the limitation of huge fluctuations in pH. It prevents it. And so that's why our blood is buffered, because we don't want these big jumps. You can see what happens when we're not buffered. What happens? We get these huge jumps.
But how about on the excess? The OH equivalent, I don't know where exactly.
So OH equivalents are like how much has reacted with it. So half an equivalent, here I'll give you an example. Let's say we started out with 10 molecules of this. Half an equivalent is where we would add 5 molecules of hydroxide, right? Let's say we added 5 molecules of hydroxide. What would happen? We would convert 5 of these to 5 of these. And that's what we call a half an equivalent. How much you need to convert half of what you have into the conjugate base. So that's what those equivalents do. That's like half an equivalent, that's 1. That would be enough to convert 10 of these to 10 of these. How many equivalents? And remember from your stoichiometry, we would write like 2 moles of this plus 2 moles of that yields whatever. That's what those equivalents mean. It's how much you have to react to get, if it's half an equivalent, that's enough to react with half of these to make it 50% conjugate base, 50% acid.
So how do you find the PI?
Okay, so then the PI, right? That's why I have to draw this. Of the PI, what's the definition of the PI? Isoelectric point.
Charge 0.
Charge is neutral. So we would look at this and we would say, what's the charge here? Well, that's plus 2. What's the charge here? Well, that's plus 1. What's the charge
0.
here? 0. What's the charge here? Minus 1. So the isoelectric point has to be the average of these 2 pKa values. Here's the neutral species, and if we don't want to be in this reaction or this reaction, we have to be at a pH somewhere in between. So what we say is, okay, here's our 0 point, so we take a pKa on either side, right? 9.5 plus 12.5. We want to be exact, we want the pH to be exactly in between those pKa values. So we add them together, divide by 2. And then we get what?
11.
Plus 9 is 22, right?
It's 11.
No, wait, no, that's not right.
No, you're right.
Is that right? 22?
Yeah.
Okay, 22 divided by 2 is 11, right? So on this plot, we should see a raised area right here. Looks pretty good to me. That's our PI. See that spot where it shoots up? It fits, even though I didn't even intend to draw it, right? It's there. It's in between these 2 positions. It's that pH in between those 2 positions. That's our PI. Here's our pKa 3, right? Here's our pKa 1. Does it all make sense now?
So if you were to ask like the nitrogen acid question, you would tell us where you wanted the buffer at.
Yeah.
Okay.
And then you have to identify it. Let's say I said I want a buffer that has a pH of 2.5. Which species, which group of acid and conjugate base is going to provide buffering? If I said pH 2.5, which one would you use?
The first 2.
Yeah, you'd want to have these species in here. Because what's the purpose of the buffer? To moderate it, right? So if we want something down here, we would want to have it these 2 species. What are you doing, Frank?
Just if you're asked to find the ratio at like a pH of 6, what pKa value would you use?
Okay. So if you have pH of 6, you're not going to have, you're going to be somewhere in here. So you're going to have completely this species right here because you went past, right? If you want a pH of 6, there's not going to be any buffering there. You went way past the buffering region, and so it's going to be completely this species because you went past that equivalency point. You might be starting to get up near that, but it's really completely all that. There's nothing going to be, you know, reacting there until you get above, until you get up into that. Right. But the thing is, if you're in this zone here, you know, you're not even adding hydroxide. Look at what the pH is doing. It's just jumping all over the place. So it's a not a good zone to be in if you're trying to buffer something. You can't buffer something. That's why we always pick. Okay, we want to make a buffer of this. What has a pKa within that range that we can set a buffer system on? Any other questions? Yeah.
Can you go over Ramachandran?
Ramachandran. Let me pull it up on the